All right, hi PyCascades. I'm Matt. I'm from Seattle. I'm an organizer of the Puppy, which is the Puget Sound Programming Python group. If there's any other Puppy organizers in the audience, can you put your hand up? There's Paul. I bring this up because we're rebooting our monthly meetup. We've done 2 of them already, and we're in desperate need of any speakers. I wrote this talk to give at one of our first rebooted monthly talk nights, and I would like to invite anybody who wants a low pressure situation to give a talk to me or Paul, and we'll get you set up for that. So let's go. My talk is titled The Rising Sea. This probably has the vibe of a somber talk about maybe climate change or something. I promise this will not be the case. I want to talk about a great problem solver from history and his approach to problem solving. So let's start with a photograph. This charming young man, this is a photo taken in the 1950s. Anybody know who this is? 0 hands for the camera. This is Alexander Grothendieck. He lived from 1928 to 2014. Any guesses at his profession? There was a hint. He was a mathematician. He may have been a sailor. That's not in any of the biographies, but it doesn't rule it out. So this is Alexander Grothendieck. He's a mathematician. He did the majority of his work between the 1950s and the 1970s. Some analogies for other fields that are of individuals of comparable stature. Mathematics has Grothendieck, physics has Paul Dirac, who created the relativistic equation of the electron. Computer science, Alonzo Church. Lambda calculus. Programming languages, John McCarthy, the creator of Lisp. Literature, Cormac McCarthy, who writes very abstract, difficult novels of great beauty. And in music, Brian Eno, glam rocker turned abstract musician. When Grothendieck passed away, he was eulogized in the New York Times, which is a periodical that the audience is likely familiar with, but also Nature, which is a scientific journal of great stature. Many scientists, this is their goal in their careers, to get a paper published in Nature. That's a career moment for them. The eulogy here is written by David Mumford, who was Grothendieck's peer, and he had this comment on the experience of trying to write a eulogy for Grothendieck. The sad thing is that this was rejected as being much too technical for their readership. The editor wrote to me that higher degree polynomials, infinitesimal vectors, and complex space, even complex numbers, were things at least half of their readership had never come across, by David Mumford. He was trying to give a sense of what this person actually did, and he found the task impossible. So this is very, very deep thinker, very deep work. If any of my friends are in the audience, this is a challenge. If you can write a eulogy for me when I die and it gets rejected, I would find that very amusing and it would please me greatly. To give a sense of his personality, I have this note. This is Grothendieck's handwriting. He wrote this in the guest book of a coffee shop that him and his colleagues frequented in the 1960s and the 1970s. I have a translation of this, but I don't speak German. I got it from that great bastion of the internet, Reddit, which speaks to its absolute, it's absolutely correct because I got it from Reddit. So I apologize to any fluent German speakers in the audience. I'm going to read it out. So what this says is Witch's Kitchen, 1971. Riemann Rock, the latest craze. The diagram is commutative. By the diagram, he's referring to this rectangle made of arrows and symbols with the little devils burning around it. In order to give this statement about the function f an approximate meaning, I had to abuse my audience's patience for nearly 2 hours. In black and white, it seems to take up about 400 to 500 pages. This is a thrilling example of how our urge for knowledge and discovery plays itself out more and more in a logical delirium that is enraptured from life, while life itself goes to hell in 1,000 ways and is threatened by final annihilation. It is high time to change our course. That last bit may be kind of off-putting, Grothendieck was his whole life a pacifist. He spent time in Vietnam during the war teaching mathematics in rural communities. I believe he had this, I don't actually know this, I believe he had just returned when he wrote this note. So these thoughts of humankind doing violence to one another was much on his mind, and he was very much against this. I want to talk about an analogy that Grothendieck had for problem solving, which he referred to as the rising sea. In his own words, it goes like this. A different image came to me a few weeks ago. The unknown thing to be known appeared to me as some stretch of earth or a hard wall resisting penetration. The sea advances insensibly in silence. Nothing seems to happen. Nothing moves. The water is so far off that you hardly hear it, yet it finally surrounds the resistant substance. This is Grothendieck's own words. His student, Paul Deline, who will play a role at the very end of our story, put it in a way that I find a little bit more compelling and a little bit more straightforward. He says, I have learned not to take glory in the difficulty of a proof. Difficulty means we have not understood. The ideal is to be able to paint a landscape in which the proof is obvious. You have to know a little bit about mathematics to unwind this. What mathematicians are trying to do is discover proofs of logical statements. That's the currency of mathematical research. And Deline is saying, we don't want the end result of that to be difficult to understand. We want to build up theory and understanding to the point where the problem evaporates, where it dissolves in the landscape that we have painted. I'm going to contrast this, as Grothendieck did, with the counter strategy for problem solving, which he referred to as nut cracking, which you should think of as like, I have a nut and I have a hammer and I just smash the damn thing. As an individual, to represent this style of problem solving, I offer Grothendieck's contemporary Jean-Paul Serre. So Serre is very famous in the mathematical community for writing textbooks that are about this thick, and for the camera, that's about like a centimeter thick. And if you've ever read a graduate textbook in mathematics, it's generally much longer than that. He gets to the heart of the matter immediately and introduces only enough abstraction and information that is absolutely necessary to solve the problem that he's trying to address. This is Serre's style. This book is called A Course of Arithmetic. All young number theorists should read Serre's A Course in Arithmetic. It somehow captures an immense amount of the spirit of a subject in a tiny amount of space. This is Serre's reputation is being able to get to the heart of matters very briefly. It was written by Jordan Ellenberg, who wrote a pretty popular pop sci book recently about problem solving as well that's very accessible. Here's Colin McLarty on the relationship between these two individuals. Serre created a series of concise and elegant tools which Grothendieck and co-workers simplified into thousands of pages of category theory. I highlighted that word simplifies because it's used in a way that only a mathematician could use it, where you take brief and efficient exposition and you turn it into gobs and gobs of abstraction. This is the ideal for mathematicians. All right, but this is a programming conference, right? What am I talking about? What's all this mathematics about? Which style makes for better computer programs is the question I want to talk a little bit about. Should we be Grothendieck or should we be Serre? As an example, I'm going to offer Advent of Code 2022, problem number 5. How many people are familiar with Advent of Code? Yeah, it rules. Advent of Code is a sequence of programming puzzles that is published every December, starting on December 1st, going to the final puzzle on December 25th. This one is about like a harbor, like a shipping harbor, where you have stacks of shipping containers and cranes need to move them around. So here is an example of that. We have 3 stacks of shipping containers. The first one has 2 containers stacked up, second one 3, third, a single container. And I've got them labeled with letters, but the letters won't be particularly important. The puzzle gives you a sequence of instructions, and it says, well, I want to move some number of containers from one of the rows to a different row. So here I've moved 1 container from row 2 to row 1. If we looked at the original state, D was in row 2, or column 2. Rows and columns, who knows? And here we have it in the first column. Here's another example. Move 2 containers from column 1 to column 3. You can see before we had D and N stacked up, and then we moved them to column 2. Or wait, I pressed the wrong button, to column 3. The actual input to this problem is much more extensive. We have about, I think I counted there about stacks of 8, and there's 9 columns. And you can maybe guess what the problem is. You can maybe guess what the problem is. We get a long list of instructions, hundreds of them. We want to execute all of them on an initial state like this, and then get the right answer, move them around correctly. That's the goal. What would our individuals say about how to solve these problems? Obviously, this isn't something they actually said. This is in my imagination. But Sarah says we should just write the code to directly solve the problem. As directly as possible, as efficient as possible. We should do it as fast as possible. Grothendieck says we should structure our data in a way that the problem solves itself. We're painting a landscape. Once the landscape is painted, what the solution to the problem should be obvious. So how does that actually work out? Well, let's kind of enumerate the concepts in the problem space that we need to model. These are the 4 I came up with. There's our instructions, individual, move X of these from Y to Z. There's all the instructions together, which I called a program. There's stacks of boxes, like our shipping containers stacked into one single column. And then there's the harbor. Harbor? I have no idea whether I'm supposed to pronounce that H, and it's making me nervous. So apologies if I didn't get it right. We got our harbor, which is all the stacks of boxes together, and that's the data that we want to manipulate. So we're going to start here. Can we start to model these concepts? What does this look like in our programming language of choice of Python? Instructions are simple. They're just data. They don't have to change. We get them, and they're the same forever. I'm a big fan of data classes, which are like structs in other languages, if you're familiar with C or Rust. I use them all over the place. So here I just created a data class to store the source, the destination, and the count. Move this number, the count, from the source to the destination. No behavior, just data. A program is a sequence of instructions, and this is easy to model. It's just a list of these instruction objects. I'm a big fan of this. This may look like strange Python, program equals list of instructions. This is creating a new type. This is called a type alias if you look it up in the documentation. I'm a big fan of this. I do it all over the place. This has no behavior at runtime. It's just documentation for how your program should work. The harbor. Now we get to some real stuff. I've written this out in a way where I haven't written any code yet. I'm just trying to sketch the landscape and fill in the details later. So what should a harbor be able to do? Well, first it has to look at an instruction and change itself according to what that instruction says to do. I made a method, I called it execute. It takes an instruction. It's going to change the data internally to the harbor in some way. Run, I can write completely. It doesn't work now because I haven't implemented execute. I'm going to get squiggly reds in my IDE, but I can write run. I know what it has to be. I just use execute. I go through all the instructions and I execute them. So that's quite nice, and I like this gradual buildup of complexity we've got going on here. Let's fill in some stuff. So how are we going to represent the data? I'm going to have 9 of these stacks of shipping containers, so I just create a list of them. I can write the execute method already. Once I have a list of stacks, it's very straightforward. I have a source, I have a destination, I grab the 2 stacks I actually care about and I name them because naming things gives you power over them. Then I take off some of the end of the source one and I put it on the end of the destination one. I've colored some of these in red. Any guesses as to why I colored them in red? You don't have to say it, just in your imagination, can you guess? Those don't exist yet. So I colored them red because in my IDE I will get red squigglies under them. It will say, you haven't defined these yet. Why are you trying to use them? This code won't run. That's good. I like that. because it tells me what I have to do next. I have to create stack, I have to create pop sum, and I have to create extend. One other interesting point here that I find is that I've used traditional names for the methods. Extend is a built-in on Python list. I used the same name intentionally because then readers of my code will be familiar with the concepts of extend and have a very good guess as to what this method will do. If you invent new names, that you don't get that like historical knowledge to rely on your readers. I think that that's powerful too. Let's do stack. A stack is a list of boxes. What a box is an exercise to the reader. And now I can write the two methods that were in red before, pop sum and extend. One interesting thing here, and I think this is very powerful, is I don't have any choice for what to do here. There's really no other way to write these methods. I've set up things in a way that every move I've made has been forced. That was the genesis of this talk, is when I was solving problems in Advent of Code, I got this feeling after some of them where I couldn't tell where I did the work, like where the hard part was. And I invite you to kind of think about that, like where did we do work? Where was the hard work in solving this problem? I'm going to count to 10 and make sure everybody gives it a little bit of thought. I would argue that the work is here. This is the important work, is thinking a little bit up front. What is the model of the problem space? What is the landscape that we want to paint? What are the entities in that landscape? Once you've set that up and you've modeled the problem space well, you're not left with much choice as to how to write the code. And I would argue that that's good. The less choice you have for writing code, the more you in the future and people who are tasked with maintaining your code in the future will be able to have very intuitive and clear guesses as to where to look for information and what needs to be modified. I like this feeling when I'm writing code that I'm just following along and I have no choice and I can vibe out to Aphex Twin or whatever I'm listening to and just like get into a flow state, right? Setting things up front in terms of these concepts allows you to enter a flow state and just write your code and it'll be clear and understandable. If you're lucky, but there is the darkness. The darkness is that not all problems are amenable to this structure, to this methodology. The darkness is this. I didn't tell you how I got this string. This is just a string. It's a text file. How did I get this and create a harbor object? I wrote all my code assuming that I had the harbor object and had the data inside of it to begin with. I didn't comment on how I turned this into the harbor object. Would you like to see how I did that? It looks like this. You may see that when I exported this to a PDF, it got really corrupted. I didn't fix it because I think it emphasizes the point that this is absolutely terrible. I'm not a good enough programmer to make this beautiful. I find that when I implement systems, the outside layer often encompasses a lot of complexity, getting the data into the system, and it's difficult to reduce that. It's just fundamentally difficult. Some systems also have complexity at their very core. If you think of like machine learning systems, like PyTorch. PyTorch is really freaking complicated, but when you work with it, you don't have to worry about that complexity. You've isolated it to the very core of your system. The middle layers should be simple. Simple is maybe a bad choice of words, but should be as straightforward as they can possibly be because you've modeled the problem in terms of concepts that are natural to what the task you're trying to accomplish. This reality actually came for Grothendieck in the end. So I'm going to close by saying a little bit about what Grothendieck was actually up to in his career. There was a mathematician named Andre Weil. He was studying the geometry of solution sets of polynomial equations. So I'm going to give a little mathematics. So I think everybody is a programmer. You probably had to take some math classes. You've probably encountered polynomials. You've probably encountered quadratic formula. You've probably plotted like parabolas and cubic curves. Is that correct? Is that a reasonable assumption? All right, you can take that way too far. And if you take it way too far, you end up with geometric questions about what these solution sets look like in very high dimensions, or if you have very high degree polynomials, or if you have multiple polynomials at once. What are the properties of like the geometric space that you get when you look at all of their solutions? They had 3 conjectures about what these looked like. They're called the Weil conjectures. They're very famous in mathematics. There's lots of YouTube videos trying to explain what these really are. There's a Wikipedia article. You can read a lot about the Weil conjectures. Grothendieck's goal in life was to prove these 3 conjectures. And he developed all of his theory to accomplish this problem. And he succeeded on 2 of them, the first 2. The third one did not fall to his methods. The third one fell to his student. You may remember Paul Deligne from earlier. He was the one who successfully closed the final Weil conjecture, and he did it by nut cracking. He just did really hard analytical work that was not abstract in any way that would be meaningful to a mathematician. It was just computation, brute force, difficult. Grothendieck was not particularly pleased with this outcome, and due to this and his pacifism and many other reasons, he dropped out of the mathematical community and moved into the foothills of the French mountainsides and retired. He spent the rest of his days drinking dandelion tea and writing prolifically on mathematics and many, many, many other topics, but not engaging much more with the mathematical community. His work has affected generations of mathematicians. He essentially rewrote completely how mathematics is done, and every young mathematician has to at least confront the changes that he made to the mathematical culture. He's, if you ask a mathematician who's the GOAT 20th century mathematician, many of them will say Grothendieck. So that's my talk. Thanks for listening, and thanks for coming to PyCascades, and thanks for hanging out in Seattle. It's a beautiful city.